I want to show you a few things that I put together. And so there's this preparing for the final exam announcement that I want to make sure you're aware of. I created this page of how to prepare for the final exam, which I'll show you in a moment. And then there's these other informations I want to make sure you're aware of. All the class videos are up. Next week, there won't be any class. Class is going asynchronous, so you can have the time to work on the final exam. You can shoot me an email or a text message anytime. And don't worry that if you're up studying and you're stuck on something at 2 a.m., just shoot me that text message. I have Do Not Disturb on, so you're not going to wake me up. So don't worry about that. So here's your reminders of things you should complete. I also want to make sure you remember that nothing in this class can be submitted after 11:59 p.m. on the last day of finals. If we go to the modules, I want to make sure you see that, first of all, you can collapse them all. If you're using it on your phone, just scroll to the very end. So here's the information for the final exam. Okay, I've got this page of how to prepare for the final exam. It's just some tips and reminders. Remember, all these live Zoom meetings is where you can find all the class videos. Here's the practice finals exams for you. On that page of the how to prepare on the final exam. So I just have a to-do list for you, just things, help you focus and maybe be able to check off some things. I always found that very helpful. And just a reminder that there's lots of places and people here to help you when you get stuck. If you have any questions, you can always text me when you're on the final exam. If you need help, if you're having trouble with your calculator, your browser, or whatever, send me a text message. I will always give you a hint of some kind. You might not find that hint helpful, but I will always give you what I think to be a helpful hint. And here's just the details for the final. Part 1 is Monday and Tuesday. Part 2 is Wednesday and Thursday. And you can take them earlier if you need to, just let me know. Part 1, I can push into Wednesday or Thursday. If you need that little bit of extra time, just let me know. Part 2, I cannot extend the time because you can't submit anything in this class after Thursday at 11:59 p.m. And that's when Part 2 is due. What I would suggest to all of you, and this is feedback I've gotten from students, is that try and do the practice test at least once shortly before you're going to take the real test. If I was a student, the way I tend to do things is I do one attempt pretty quickly. Do one like this weekend, do it soon. Or even this week, ideally. Ideally, it would have been done last week. Do it the first attempt as soon as possible. And then that first attempt will let you know kind of where your weak spots are. Will let you know if you need to make some additions to your notes or make some notes to yourself or go and practice some more problems in a specific lesson. And then do some practicing and catch up on some material, and then go back and take it a second time this weekend, maybe Friday or Saturday. And then hopefully your score will go up and you'll see, okay, well, that didn't work. And for that second one, I would actually time myself 2.5 hours for the final exams. So I would give myself 2.5 hours to take those practice tests. And if I'm not able to get them done in those 2.5 hours, then I would see what I can do differently. And then I would take the practice final a third time, a couple hours, if not right before I take the real final exam. All right. And that way, all that material is fresh in your head because the questions are all meant to be a little complimentary. It's not meant to be surprising. The idea is to have it fresh in your head. If you have remaining attempts on your Unit 1 practice test or Unit 2 practice test, also go and do those remaining attempts as a good practice, because the number one mistake people do when they're studying math is reading through things. The test isn't about how well you can read. The test is about how well you can do the math. So in order to study for math, you need to actually do practice problems. Okay, don't just read through the problem, actually do the problem. The mistake people make is going to the answer key too soon. If you're struggling with a topic, and you're unsure how to do it, and you're trying to think through it and trying to remember what you did, that means you're doing it correctly. That's how you actually study, and that's how you learn math, is that struggle is where you're learning. Just because you're struggling with something in math in particular, but with every topic, if you're struggling with it, that doesn't mean you're bad at it. That just means you're learning how to do it. I struggle with math as well. I've been wrong a number of times, even in this class, even this semester. This is hard for me too. There's a lot to statistics. There's a lot to it. I only know just a little bit deeper than you folks know. Math is hard. Struggling with it does not mean you're not good at it. It just means you need to spend more time on it. That's my soliloquy for the day. I'm reminded of one more thing I want you all to know. This is not a great way to learn. I think everybody could agree with that. I'm glad that you're here at a community college so we can get a little more of a relationship going. As you know, at the public universities, classes, just even in person, are much larger, maybe 150 people in one class. You have your main instructor, and then you get sorted off into groups of 20, 30 people, and you might have a graduate student as a teaching assistant. But now that we're in COVID times, I will tell you that one of my nurses and I were talking about school. Her daughter just started as a freshman at UC Berkeley. She was telling me about her Calc 1 class that she's taking this semester, and I am not exaggerating. There are 2,000 people taking that calc class this semester with one online instructor. In our college, all three of our colleges in this district, we have not increased any of the class sizes. We still have the same number of students we would have in the in-person. I personally think that you got better instruction here than with 2,000 other students at a four-year university paying all of that money. So I'm not going to see you next week. I appreciate all of you, and I hope that you are staying safe and that your families are staying healthy. Okay, I'd like to give a quick overview of Unit 3. So you have reviews for Units 1 and 2, so that's why I'm kind of focusing on Unit 3. Let's start with Unit 3, Lesson 18. Okay, Lesson 18 was confidence intervals. Lesson 18 was kind of the black sheep of the Unit 3 family because everything else is a hypothesis test. Remember, the whole point of confidence intervals is we use a sample to help us gauge a range of where the average population is or where the proportion of population lies. Okay, so we use a sample to learn about a population. Again, there's two different ways we could do this. We could do a proportion, so we could find the proportion of people in the U.S. who would vote for Biden. For example, what that looks like is if we have the poll that showed 43% were for Biden. Okay, we use that margin of error to come up with that margin, to come up with the interval. Okay, so if it's 43% for Biden, that's plus or minus 2%. Okay, which means the population, the proportion of people in the population who are going to vote for Biden is 43%, give or take 2%. Okay, and we always say we are 95% confident or 99% confident that between 45% and let's just say between 41 and 45% of people will vote for Biden. Okay, and remember, we got those numbers because we got 43 plus 2 is 45, and 43 minus 2 is 41. That's where we got these numbers from. Okay, so this is your translation. And that 95%, it's important to remember that confidence interval, whatever confidence interval we're using, 95% is the most common, but the confidence interval means that that's how often we will be correct. It's not saying that 95% of the people are voting for Biden. It's saying that 95% of the time, 95% of the polls are going to show between 41 and 45%. Okay, so 95% we're correct 95% of the time, or the confidence level. And I will post these notes, okay? So 95% confidence interval means we are going to be right 95% of the time and that we're going to be wrong 5% of the time. And we can do this for means or proportions. So here we found the proportion of voters, but we could also find, like, for instance, average height. Okay, and we have two different calculator functions that we're using on page 6 of lesson 18 worksheet. Okay, and that looks like this. Okay, so proportions, we use a 1 prop z interval, and for means, if we're trying to find like the average height or the average weight, we're going to use 8t interval. Okay, and remember this, so this part is similar for what we were doing with the rest of the unit with the hypothesis testing, is that proportions go with the z and the means go with the T. And then also remember this int stands for interval, as in confidence interval. We'll go on to hypothesis testing. We have 5 hypothesis tests now. Starting lesson 19 through 23 are 5 different versions of the hypothesis test. So lesson 19 is talking about has a mean or a proportion for a given sample changed from what it was in the past. So has the proportion of voters changed from the poll we did last month? Or is it more than that? Are more people voting for Biden or less people voting for Biden? And remember, the whole point of the hypothesis tests is to gauge, is what we see indicative of the population, or is it just because of the way the sample played out? Because we all know samples are very different. Every sample you get is going to be different. How to tell this is one sample is, remember, you will be given information for one sample. And by that information, I mean specifically how many people were in the sample and how many of those people did or behaved a certain way or did something. So the total number of people in the sample, that's N, and how many were successes. And remember, a success is defined whatever it is that you're talking about. Actually, let's go back to lesson 21 real quick. I'm going to remind you on lesson 21, I have this lovely decision tree. And I put this decision tree on the practice final exam and also on the actual final exam. So you will have this. You can use this to help you remember or to help you figure out what calculator function you should be using. And remember, on the back of that page on lesson 21, I give you a whole bunch of scenarios, like 5, 6 different scenarios, and you had to go through and figure out which type of test you would be using, which of these scenarios we were going to be using. That's how what you're going to have to do for the final exam. For the chi-square unit 20, lesson 23, I will tell you which chi-square to use. Okay, but for the hypothesis test, you do need to figure out which of these different tests it is that we're talking about. I don't give you this on the final exam, though. That's just clues to help you remember what's happening. For the one sample lesson 19, we're here on this part of the tree, so you would need to figure out, are you looking for the mean or the average for something, or are you talking about a proportions? And remember, the whole idea of the hypothesis tests is that you're told things are a certain way, but you believe they have changed. You believe that it's increased or that it's decreased or that it's just different. And so what you need to do is you need to go gather a sample, and you use that sample to run a statistical test to determine if the differences you saw in your sample are just a factor of the sample or if things are really different. That's the general idea for the hypothesis tests. So is the difference meaningful, and we call that statistically significant, or is it just a factor of the specific sample we gathered? For all of these, we're figuring out the same steps. And step 1 is we develop a null and alternate hypothesis, okay, where your alternate hypothesis is that things have changed, are not equal to, less than, or greater than. Step 2 is we look at a sample, we collect some evidence, okay, and this always comes from the sample. Step 3 is we calculate the probability. And this probability is what we call the p-value. The probability of getting a sample that looks like ours, assuming things are how they say they are. So assuming HO is true. Step 4, we compare the p-value to our level of significance, okay, which we call alpha, and it's usually 5%. Okay, and remember that alpha is how often we want to be wrong. Okay, just like before with those confidence intervals, the alpha is how often we want to be wrong. And remember, we have a saying, if the p is low, that hoe's got to go. Technically, that's what we consider the step 5, the conclusion. So let me just be consistent. Okay, so we compare the p-value to the level of significance, and we do a conclusion. Do we reject HO or not? To determine that, we use this phrase here. If the p is low, that hoe's got to go. And remember, if that p is low is meaning, what that means is if p is smaller than alpha, then we reject HO. Or you can say if alpha is bigger, we're rejecting HO. And the reason why I wrote it this second way was because on the worksheets, That's how I ask you the question. I ask you which value is bigger. Upon reflection, it would go more with this phrase if I asked you which value is smaller, but worksheet's already done, so that's how we were rolling. For that question on the worksheet, which value is bigger, P or alpha? Anytime you put an alpha as the bigger number, that means we are rejecting the whole. So that's the similarity between all 5 or 4 in this class, all 4 of these hypothesis tests. So let's scooch back to lesson 19. We're looking at, has the mean or proportion from one sample changed from what it was in the past? But I also wanted to point out, because there's another aspect to lesson 19. We learned this, but then we also learned about types of errors. You will be asked to articulate what a type 1 or type 2 error is. Those are on page 6. Basically put, a type 1 error means that you rejected the null when you should have kept it. Sometimes we'll never know what type of error we made. Sometimes you might figure it out 20 years later. Sometimes you might figure it out 2 hours later. Generally speaking, when we're making those decisions, we don't know if we're right or wrong. It's only hindsight, once the things play out, that we can figure out if we were right or wrong. Okay, but in the moment, you don't know. Okay, and the type 2 error is we kept the null and we should have rejected it. And you'll remember my favorite example of this lesson is the food poisoning. So let's go on. We skipped lesson 20. So then we went on to lesson 21, which in lesson 21 is we're comparing 2 samples. Is one bigger than, less than, or different from the other sample? And this actually, no, that's not accurate, this last bit. So really, we're comparing 2 samples. So examples of comparing 2 samples is, are there a higher proportion of dog bites in Philly versus in Cleveland? Do postal workers get bitten more often in Philly versus Cleveland? And so this would be a proportion. We have 2 different options. We have a average and we have a proportions. Okay, so this is a proportion. Another example would be, do children get more REM sleep or REM sleep than adults on average? And that then would be means. So the nice thing is, if you have this graphic here, that will really help you, because I've written it 2 different ways. You can think of it in terms of the samples, but if you know what lesson that problem that you're working on comes from, that narrows it down. Because I put the lessons here, lesson 19, 20, 21, 22. And remember, we did not cover lesson 20, so you can just cross this one off. You know it's not going to be that one ever, because we skipped this one. The hard part is to figure out, is there 1 sample or is there 2 samples? And remember, for this, you will always be given information for 2 separate samples with how many people were in each sample, N and X. So that's how you can tell the difference between 19 and 21. Is, are you given information for 2 very specific samples? And generally speaking, it'll be 2 different categories, like 2 different cities in one example, or adults versus children in another example. Okay, and you'll be given those specifics. If you haven't done this last page yet on lesson 21, I would suggest you do this practicing of reading through the example and using that to determine what test. This is really good practice. And I'm not suggesting you try to memorize it, but being familiar is going to go a long way to helping you figure out what you should be using.
How do you know the difference in failing to rejecting the null and when to reject the null?
Glad you asked. All of these circumstances follow these same steps, including the rejecting the whole. And all of these, we're calculating a probability, finding a p-value. We're comparing that p-value to our level of significance, and we're making that conclusion based on this phrase here. If the p is low, that hoe has got to go. So if the p-value is smaller than the alpha, then we're rejecting the hoe. That is probably the hardest part about all of this. Well, okay, the setup is also hard, but it's down here. It's this step where most people make the most mistakes. And this P is low is referring to lower than this level of significance. Just to clarify here, lesson 19, we have 1 sample. Lesson 21, we have 2 samples. Lesson 22, we have 3 or more samples. Okay, so lesson 22 is where we were doing the ANOVA. And the question with the ANOVA is, we have 3 or more samples. Are they different from one another? Well, I'm sorry, my writing is so terrible here. With these ANOVAs, the HO and the HA are always the same. With the ANOVA, the HO is that there is no difference at all between these samples. And that is in proportions or in averages. Either way, ANOVA is always independent. So yeah, it could be samples or proportions or means. The assumption is that there is no difference. And so you could think about like those dog bites. We compare dog bites from Cleveland and Philly. We could add in San Francisco, and then all of a sudden it becomes an ANOVA. Or we could compare the amount of REM sleep that children get and middle-aged adults and elderly people. That becomes an ANOVA once you add that third or fourth category. Or if we were doing on-time rates of airlines, we could compare Delta and American and Southwest and Virgin and Sun Country. We could compare all 5 of those, and that's an ANOVA. So anytime it's more than 2 samples and you're comparing to see if there's a difference in a proportion or a mean, that's when we're doing an ANOVA. The nice thing about the ANOVA is the null and the alternate hypothesis for every single problem is exactly the same. The null is that there is no difference between these samples, and the alternate hypothesis is that at least one of them is different. The important thing to know with this ANOVA is that we are not determining how they are different. No matter how many samples we have, we're not determining is one bigger than the other. These 2 might be the same, these 2 might be the same, and this might be somewhere in the middle. One could be bigger and the other ones could be the same. One could be smaller and the other ones could be the same. Or there's a whole bunch of different ways this could play out. We are not trying to determine how they are different. We are just trying to determine if they are different. That's a really important distinction. Let's go to lesson 23. We've got 2 different things happening in lesson 23. Okay, we've got the goodness of fit test, and we have this test for independence. The goodness of fit test is kind of more like lesson 21, and it is compared to before. Has the proportion changed? Another way to think about this is, I'm going to talk about that M&M example that we did in class. I expect a certain, with the M&Ms, I know what proportion of each color M&M fills the bags with. But what I see in my sample is something very different from that. Does that mean, or does that suggest that the company changed the proportions? Or is it just a factor of the sample that I have? That goodness of fit, what that is referring to is, are the proportions close enough to what we're expecting? That's what goodness of fit is talking about. With the M&Ms, I'll write that example up, is that I expect the proportions of colors to be one thing, but my sample is very different. Does this suggest that the proportions have changed? Hopefully you can see some similarity between this and the ANOVA, right? ANOVA is comparing, again, 3 or more different categories and saying, are these statistically equal or not, these different categories? And that's all it is are they statistically the same or are they not? In the goodness of fit, it's the same idea. I expect a certain level, I expect the proportions to be one thing. What I'm seeing is different. Are these statistically the same or not? This is still a hypothesis test. And in this hypothesis test, like the ANOVA, my null and my alternate hypothesis are always going to be the same. Okay, the null hypothesis is going to be the proportions are what I expect. Even though our sample is different, we're assuming that it's just a factor of the sample. Yeah, I got a wonky sample. Like with my M&Ms, I had so few reds left in that box. Why were there so few reds? I wasn't picking out any specific colors. I was just randomly pulling out M&Ms when I was eating that box. That doesn't mean that I started out necessarily with less M&Ms. They could have been stuck into one corner of the box. The alternate hypothesis is that the proportions have changed. For the goodness of fit test, these are always going to be my null and alternate hypotheses. The goodness of fit is always going to be a proportion because that's what the fit part of this is, the goodness of fit. I expect the M&Ms to be 24% blue, 13% red, etc. My sample looks different than that. Is my sample far enough away from what I expect that I can say the proportions have changed or not? Ella asks, how do you know the difference between using mu or p for the null and alternate hypothesis? And that is a great question because on your test, you're going to be given an options and you might have the right numbers, but you need to be able to determine if you should be using p or if you should be using mu for your null and alternate hypothesis. One thing you do know is they're always going to be the same, but let's go back up to, let's go here. I'll squeeze it on here. For this one, if you see, for instance, the proportion of people who eat red meat, that's going to be a P. But if you see something like the mean weight of a bunny, mean or average, that's going to be a mu. You need to know that P versus that mu for two things, for how to write your null and alternate hypothesis, but you also need to know it for which test to use, because in each lesson, there's two different options. Okay, the only lesson that only has one option is the ANOVA, and that's when you've got 3 or more samples, and that should be 3 or more. You can add that here. If it's means, you're talking about mu, and if it's proportions, you're talking about p. Okay, you may want to just add that to your notes.
How are we sure when we do or do not have enough information to accept or reject a hypothesis? Because I know that's usually listed at the end of a lot of these problems.
It all comes down to here, this conclusion. I'm going to tell you right now, we never accept the null. That is an option. That's a trap. Don't ever accept the null hypothesis. We either reject it or we don't. Accepting the null hypothesis would be like the courts finding somebody innocent. The courts never find anybody innocent. Doesn't mean you didn't do it. It just means that there's not enough evidence to show you did do it. What we do is we compare. This is how we determine if we reject it. And I'm going to add a note here that we never, okay, don't fall into my trap, folks. We never accept the null. We have one last little bit to go over, and that is the chi-square test for independence. And the chi-square test for independence is the second part of lesson 23. What we're looking for is just determining if the two variables are independent or dependent. How you know you're on the chi-square test for independence is you will be given a two-way table. So remember the example we did in class last time was, is age independent of whether or not you're likely to buy American products? Or is age independent of what music you listen to? And we can use this test for independence in order to find that out. And I didn't mention the calculator stuff. Let me add that in real quick. For this chi-square test for independence, what we're using is, remember, is we put the data into a matrix, and then we're using stats, tests, and it's C, chi-square test. Okay, and up above, for the goodness of fit, we put the observed, and that's your sample, into L1, and we put expected into L2. If you get these backwards, that's no big deal. You just got to tell the calculator which one you put it in. It's totally okay for these to go into even L3 and L4. Okay, you just got to tell the calculator different. And I just say L1 and L2 because calculator defaults to observed in L1 and expected into L2. Expected is the expected values based on the proportions we should be seeing. And then as we do stat tests, and that's D, chi-squared GOF test. And that GOF means goodness of fit. One thing I forgot to mention is in order to do that, you will need degrees of freedom. I forgot to add that, which in the calculator are noted as DF, and those are the number of categories minus 1. So I have 6 colors of M&Ms, so degrees of freedom is 5. Okay, so that is the end of class. Remember that I'm here for you for the next week. You can always text me. You can email me if you have questions anytime. Okay, day or night, I'm here for you. NetTutor is here for you. The DVC Math Lab is here for you. NetTutor runs 24/7. So there's lots of resources available to help you. Happy studying and good luck. And congratulations again, you guys. I'm very happy for you. I'm very proud of you. I'm glad you were here this semester and good luck. Other than that, congratulations. Enjoy the rest of the afternoon.